Hello friends. In the last video, we discussed the concept of slope of a line, also called the gradient of a line, and we described it using two approaches. The algebraic way, when the coordinates of 2 points are given, then the slope is simply delta y by delta x. Or the geometric way, when the inclination or the angle which the line makes with the positive direction of the x-axis is given, then it's simply tan of that angle. Right? And we asked a question, why is this concept of slope so important to us and how can this be useful? So in this video, let us try to get a basic idea of how powerful and convenient this concept of slope is in connecting the geometry of straight lines to algebra. Now, one of the most beautiful and the direct application of slope is the fact that the slope of a line can be used to prove the collinearity of three or more points. Now, previously, to prove that 3 points were collinear, we either showed that the area of the triangle formed by these 3 points is 0, or we use the distance formula, that is this distance plus this distance is equal to the total distance. Now in these two methods, we had some calculations and operations, right? We had to multiply, take the square root and etc. Now what if we had 4 points? Then showing collinearity will become slightly challenging. But let me tell you that the slope of a line is a way more intuitive way to see the collinearity of 3 or more points. Now we know that slope of a line is a constant for a given straight line. So you take any 2 points in the line and you find the slope, you should get the same value, right? So if you have to prove that 3 or more points are collinear, then you just find the slope because of the first 2 points. That should be equal to the slope because of the second and the third point, and that should be equal to the slope by taking the first and the third point, right? So the slope of AB is equal to slope of BC is equal to slope of CA. And this is very easier to remember, right? And even the calculations are pretty simple because slope is nothing but a difference of y coordinates divided by a difference of x coordinates. Now, slope can be useful in many other ways. Now, from the definition, as the name suggests, slope describes the steepness of a line, right? So it gives some information about the inclination of a line. So that's why it can be used to compare the inclination of two given straight lines. Now, suppose you have two straight lines in the coordinate plane. Now I'm telling you that the slope of these two lines is 2 and 4. Now can you tell me which line has a slope 2 and which line has a slope 4? Obviously, the steeper the line, more the slope, right? So obviously this line has a slope 4 and this line has a slope 2. Now moving forward, let's say we are given two non-vertical straight lines here, whose slopes are m1 and m2. Now why are we stressing on this particular word non-vertical? Because vertical lines do not have a slope defined. That is why, right? So whenever you're given that a line has a slope m, you should assume that that line is non-vertical, right? So anyways, we have two lines here. Now let's assume that these two lines are parallel. Now if they are parallel, they should have the same steepness. So they should make the same angles with the positive direction of the x-axis. So obviously they should have the same slope, right? So m1 is equal to m2. Now this is the condition for two non-vertical lines to be parallel, right? Their slopes should be equal. And conversely, if the slopes of two lines are equal, then obviously they should have the same inclination and they should be parallel, isn't it? Now what if the same two non-vertical lines with given slopes m1 and m2 are not parallel but rather intersecting at a particular angle alpha? Now can we find the relation between m1 and m2 using this angle alpha? Yes, we can. Now what's worth observing here is that when two lines intersect, then they form two pairs of vertically opposite angles. Right? So if this angle is alpha, then the vertically opposite angle will be alpha. And obviously the other two angles should be 180 minus alpha each, right? So the sum of any two adjacent angles is always 180 degrees. Now let's try to apply some geometry here. Now you can see a triangle that is formed by the two straight lines with the horizontal x-axis. Now assume that the angle between the lines inside this triangle is alpha. Right? Now I'll assume that m2 is the steeper line. So the inclination of the first line be theta 1 and the inclination of the second line with the slope m2 be theta 2. So by definition, m1 should be tan theta 1 and m2 should be tan theta 2. Right? Now focus on this triangle. Now here theta 2 is an external angle to this triangle. So it should be the sum of the two opposite interior angles, which are alpha and theta 1. So we have theta 2 is equal to theta 1 plus alpha, or rather alpha is equal to theta 2 minus theta 1. But since we have some information about the tan of theta 1 and tan of theta 2, let us apply tan on both sides. So we have tan alpha is equal to tan theta 2 minus theta 1. But mind you, you can only do this if alpha is not 90 degrees, because tan of 90 degrees is not defined. Right? So this statement is valid only if alpha is not 90 degrees. So we have tan alpha is equal to tan theta 2 minus theta 1. And if you use the expansion for this, that is tan A minus B, you get tan theta 2 minus tan theta 1 by 1 plus tan theta 1 tan theta 2. So if you substitute for slopes, you get tan alpha as m2 minus m1 by 1 plus m1 m2. Now this is an equation which gives us the angle between the two lines in terms of the slope of the two lines, provided the angle is not 90 degrees. Now clearly, if m1 is equal to m2 here, you'll see that you'll get tan alpha is 0 or alpha is equal to 0, which means that the two lines should be parallel. Now here we have found this angle between the two lines, which is formed between this triangle with the x-axis. Now suppose you want to find the other pair of vertically opposite angles, then it's simply 180 minus this particular angle, isn't it? Because adjacent angles are supplementary when two lines are intersecting. Now what's interesting here is even if you don't know which line is steeper, you can still use this formula. Now suppose m2 was greater than m1, then you get a positive value for tan alpha. That means alpha is acute. That means this particular angle inside the triangle is acute. Now suppose if m2 is less than m1, then you get tan alpha is negative. That means alpha is obtuse. That means this particular angle inside the triangle is obtuse. Now say someone asks you to find specifically what is the acute angle between two given lines of slope m1 and m2. Then you know that the tan of that acute angle should be positive, right? So you just take the modulus of this particular expression, then you'll get an acute angle. And if you want to find the obtuse angle, then you just subtract this acute angle from 180 degrees. Now friends, observe that we found this particular expression for the angle between two lines whose slopes are given as m1, m2. But this expression is valid only if alpha is not equal to 90 degrees, right? So what if the two lines are intersecting at right angles? Then what is the condition between their slopes? Let us try to see. Now if we have two non-vertical straight lines with slopes m1 and m2 which are intersecting at right angles, then as usual again we see that there is a right angle triangle formed with the x-axis. Now let's say the inclination of the steeper line with theta 1 and inclination of the other line with theta 2. Now it's again clear that theta 2 is the exterior angle to this triangle, so it should be equal to 90 plus theta 1. Now what we'll do is we'll just take tan now. We have tan theta 2 is equal to tan theta 1 plus 90. Now what is the formula for tan theta 1 plus 90? Can we reduce this? Tan theta plus 90 is sin theta plus 90 by cos theta plus 90. And sin theta plus 90 is cos theta. And cos theta plus 90 is minus sin theta. So this should be minus cot theta, isn't it? So tan theta 1 plus 90 is minus cot theta 1, which is minus 1 by tan theta 1. Now if you replace tan theta 2 with m2 and tan theta 1 with m1, you get m2 is equal to minus 1 by m1, or the product of the slopes m1 m2 is equal to minus 1. Now this is the condition for two non-vertical lines to be perpendicular in terms of their slopes. Now please try to remember this. This is very important because we're going to use this extensively throughout this chapter. So friends, it should now be obvious how the concept of slope can be used to compare the orientation of two given straight lines in a plane. Now given the slopes of two non-vertical straight lines as m1 m2, then you can tell if they're parallel, if their slopes are equal. You can actually tell if they're perpendicular if the product of slopes is minus 1. And you can find the angle between the two lines if they're intersecting at any other angle by this expression. Right? Now note that these conditions are two-way, in the sense if you know the condition for slope, you can tell about the orientation. And if you know about the orientation, then you can get the condition of slope. Right? So we'll end the session here. The next time we'll take this understanding of the slope further and we'll try to derive various algebraic equations for a straight line in the variables x and y. So until then, let us summarize. The concept of slope can be used to compare the inclination of two lines. The line with the higher value of slope will be steeper than the other. 3 points A, B and C are collinear if and only if the slope of AB is equal to the slope of BC is equal to the slope of AC. Two non-vertical lines are parallel if and only if their slopes are equal. Two non-vertical lines are perpendicular if and only if the product of the slopes is minus 1. If two non-vertical lines are intersecting at an angle alpha, then the angle alpha can be obtained by the expression tan alpha is equal to m2 minus m1 by 1 plus m1 m2, where m1 m2 are the slopes of the given two straight lines.